Good morning, students. Hopefully you're enjoying the cooler weather. I've got a long sleeve shirt on this morning, so I'm enjoying the cool weather. But good or bad, it's what we have right now. Um, what we're going to do this week is complete the work on the series, which we've been doing for the last several lectures, to finish up the very important section 10 of chapter 9. So I've got still a lot to say about that. And then, of course, we'll move into chapter 10. Now, our fourth test will actually be at the early part of next week. So you'll be able to get your test done in the early days of the week. And then, of course, there'll be homework that will be due and all, unfortunately, but hopefully you'll be able to get that out of the way before you take a little bit of time off with your winter break, or I guess it's like a fall break. So I know in the early college high school, you all will have the week off, but of course we will be having class at least for the first part of the week. And so I'll give you more information about that as the week ensues to keep you uh, abreast of everything that we're doing. So what I want to do today is to go ahead and share my screen and start with the end of the story, so to speak. There's a famous journalist called Paul Harvey, and he says, now here's the rest of the story. Well, that's basically what we're going to do today. And I'm certainly dating myself by making that reference, but it's good. So what we want to do, and I want to actually write this down. I've shown it to you many, many times, but I just want to go ahead and write down these theorems. One we've already proven, and these are so important, they're worthwhile just to write. So this is theorem 9.22, which I've stated several times, and this is the form of the convergent power series. So we know what it is. The main thing that I want to do, let me adjust this just a little bit. So I got, there we go. Power series. If F is represented by a power series and we'll write it in the standard form. This is just like what we did with the Taylor polynomial. And so we use the standard coefficient A sub n centered at C, or expansion point C, for all x in some open interval containing C. Now, of course, we already know about the interval of convergence, and so this is basically stating things that we're very familiar with. You know how to compute that. You know lots about series, which we've already talked about. But this is kind of like the linchpin. We know now, at least from our work with Taylor polynomials, that the coefficients have to basically be set up in terms of derivatives of f. So we can't get power series unless the function has some really good behavior. So again, the coefficients a sub n will be the nth derivative of f evaluated at c divided by n factorial, as you well know, and therefore f of x is basically the infinite Taylor polynomial, or the Taylor series. So basically, again, we already know this. We did the computation with the derivatives, setting them equal, and then basically evaluating it at C. And one by one, we got a sub 0, we got a sub 1, we got a sub 2, we got a sub 3. And so, of course, if we extend that, then basically what we're saying is that the coefficients won't change. We just keep going, we keep going, we keep going. There's no way to disassociate these coefficients from a convergent power series. Now, when we go to the next step, like for instance, we're done with this. How do we go to the next step? For instance, what is the thing that tells us, for instance, if we have e to the x, or if we have sine x, or even the binomial theorem, which we're going to spend a lot of time on today, how do we know that this convergent series actually is this function? That is, when we have the convergence that we have basically here within the interval of convergence, how do we know that it's actually equal to f? I mean, it could converge, but what tells us that the function to which it converges is actually f? We can set up the polynomials, and we had a really good idea with that, and we didn't really question, as long as we could keep some kind of control over the remainder term. And we were able to control that for many of the functions we worked with. And so that's exactly what we have to do now for the infinite series. So let me write this down. This is the next result that, again, is kind of the focal point of what we're doing. Now, we're going to find that this particular result is not always something we can apply easily. So we might have to try other techniques. But what I have here is the following. Let I be the interval of convergence for a power series representation of f of x. And so we think of fixing x and I. We have to do that for the proof. If now we think of the Taylor polynomial, f of x equals the nth Taylor polynomial plus its remainder. So we know we can do this as long as f is well behaved. We can do this. And the other thing that you're probably thinking of, the limit as n approaches infinity of the remainder term is 0 for each x and I. Then the idea is that as we pass to the limit, this converges to 0, and all that's left is the so-called infinite Taylor polynomial. Then indeed, f of x equals this. So when you think about this, some students get a little perplexed and say, okay, well, basically, Professor Ron, what you're saying is that we can always do something like this. We can create these coefficients, and we can figure out an interval of convergence, okay, and be happy with that. But the one last ingredient that says, okay, you're actually working with this function. That is, this equals this, is this item. This is just one way of looking at it, is this particular item here. So in many cases, if we can show this, then we can be assured that if we're in a physics class or an engineering class, or we're trying to build our own calculator, that the calculator is going to work and not produce output for something else. So in physics, engineering, say mathematicians and all always need approximation techniques. And so what we're seeing here is that this is a valid way as long as we can actually show it to actually be able to write this with confidence. Now, of course, if we're dealing with the geometric series and things like that, we get all of that for free. That's really nice. And then we know that if we had done it this way, it would be fine. But the geometric gives us convergence and everything. I mean, that's such a blessing in mathematics that we have the geometric progression. It's so convenient and so indispensable. It's like we look at the geometric progression and we think Pythagorean theorem. It's that important to what we do. So what I wanted to do here is just share a little bit of insight with this. Why? And it's real simple, but I want you to know this. So what we're going to do is we're going, like I said here, fix x in I and consider, we're just going to write a partial sum based on these coefficients. So we take this and we write a partial sum. So k equals 0 to infinity, excuse me, the n, not infinity. Yeah, we haven't passed to the limit yet. So we'll use k now that we have the partial sum. And we'll evaluate at c. Remember when we do the Maclaurin series, c is 0. We do a lot of those. Those are very useful to us. Of course, I'll keep the k's here. Creature of habit. So again, we've got this partial sum. Now, what we want to do is think about the fact that with this partial sum here, this actually corresponds to the Taylor polynomial. So you knew I was writing that, but it smoke and mirrors, right? We've got this Taylor polynomial here. So now we can actually rewrite things. That is f of x minus r, that is the remainder, will be equal to the Pn of x, or the Taylor polynomial. So then Sn of x, which is this guy, I think I always like number theory and analysis and topology, but it's a love-hate relationship, because as you learn more and more, you want to know more and more, so you work twice as hard. So now basically we get f of x minus the remainder. Now this is basically the argument that we need. We're seeing basically the connection here from Taylor's theorem. I guess if we have to think about something being very important to us, the whole concept and theoretical device called Taylor's theorem is what makes any of this work at all. So now what we want to do is pass to the limit. So for instance, consider the limit as n approaches infinity of Sn of x. So we'll just take the limit of this. Well, I'm pointing to this, so back in your notes, take the limit of this. Now, when we take the limit, and this is kind of a fancy way of doing it, making an infinite series, right? So that's going to make this into an infinite series. And then we can pass to the limit right here for this part. Now, if we look at this, we've got this here, but let's just go ahead and work out what this is. This is just the limit of a difference or a sum, so we can break it up. But now, of course, the f of x is independent of n, so this is just a constant relative to n. And then by hypothesis, this is 0. So f of x minus 0 is f of x. So equivalently, the infinite series, now we can just let n go to infinity. So now we can just write it with n or keep the k, it doesn't matter. We like the n's. So now there's no ambiguity here. We don't have a partial sum, so we can just go back to the n. Yeah, with the binomial theorem, we'll have k's and n's, and that's unfortunate, but it's the nature of what we do. Of course, I've got to go back to the n's, and I want to stick with the k's. So now the infinite series here, which again, we just write with the n's, or you can stick with the k's here, doesn't matter, whatever letter you use, there's only one of them, no problem. This is indeed f of x. So this is a way of basically verifying that the series that we actually create is what we have. And so indeed, it is true what I've been saying all along. Every convergent power series is its Taylor series, because we think about, this is what we think about as we go back. These were the notes. Again, you find these on Blackboard, another version of these, but we start out with the fact that if we have a power series that's worthy on some interval, in this case containing C, then this must be the case. This must be the case. So we're thinking, okay, so if we just kind of think about this going backwards and then just look at it from the Taylor polynomial standpoint, we end up seeing that everything is actually the same. We can't get away from Taylor's theorem, so to speak. But we always have to verify that this indeed is true. And if we can't verify this, then we basically have to say, okay, well, there's got to be some other way to show that this actual infinite series is the function. And that's a very subtle statement. And that's one thing about infinite series and convergence that makes real analysis very difficult. The idea is that I think a lot of you all have done very well with the initial work here in what we've been doing, and found that as you look at things, everything that we work on is very connected. That is, as we move from one piece to the next. And so what I want to do at this point is take an example of this and see how it actually works with this theorem. So here's an example of one of our friends. And what I've done is written up how we would actually prove this. I've got a hangnail, and of course, being a church organist, there we go. I've got to get rid of it before it drives me crazy. There we go. That's one thing, kids. When you play musical instruments, especially organ and piano, the fingernails have to be short, but you have to worry about cuticles. And as you work your technique, it's the craziest thing in the world. I've actually worked with instrumentalists before, and I say, well, you need to cut your nails. Oh no, I'm going to do this anyway. And I said, well, if you want to play Bach and you want to play the classics, you've got to have short nails. So that's one good thing for Professor Ron. My nails are always clean because I don't have any choice. So I get that by default. A little instruction about Professor Ron's history, and that's always been since the third grade. So I think most of my family decided that there would be some way I would manage to balance my talents in mathematics and music, and it was difficult to do, but it was worth it. So whatever talents you have, you learn to balance them because quality of life is essential. Now, what we want to do here is look at our friend f of x equal e to the x. So let's just say that we wanted to show that from our little list here, that is, we go to our list and we have e to the x here. We have 1 plus x, x squared over 2 factorial, x cubed over 3 factorial, etc. That works for all real numbers, okay? So basically, if we accept this, we should be able to actually verify. So when we look at this, we first note the following. That is, if we take derivatives of any order, and that's why this remainder theorem actually works well in this case. If we take derivatives of any order of e to the x, we just get e to the x. And since these are functions, we can do compositions, add and subtract, so we don't have to do this for everyone. That's the beauty of this list that we generate. And so if we think about this like the last problem, then if we wrote the partial sum as we did in the proof, it would look like this, just to kind of fill in some details. So we would have, for instance, like, say we're focusing on the Maclaurin series. We have the kth derivative evaluated at 0 over k factorial. And then, of course, x minus c would be x minus 0 to the k. So that would be our nth partial sum, so to speak. Now, of course, if we look here, this is just always e to the 0. So what would this give us? So we had e to the 0 over k factorial, x to the k. And of course, e to the 0 by definition is 1. So what we see here is that now we get that nice progression. We get what? 1 plus x squared over 2 factorial. Keep going all the way to where k equals n. So this is what we see in the list. Now again, what's interesting about this is that these derivatives are valid for all real numbers, and we just basically now want to look at the theorem and verify this. So now when we look at this, we're thinking, okay, well, that was easy enough. So what does the remainder theorem look like? So recall, one nice thing again about analysis is that when it works, it's fine. And of course, if it doesn't work, you have to get creative, like we are going to have to get with the binomial theorem. So the remainder theorem, or the remainder term, so we'll say there exists z between, that is of course up here. Now let me just fill in the details. Fix x in R. And so the idea here is we just think about the proof. We fix an x, and then there is a z between c, which is 0, and x such that. So the remainder term is the n plus first derivative evaluated at z divided by n plus 1 factorial. And then we have x minus c, or just x, to the n plus 1. Now, when you think about this and you consider basically the fact that we look at this and say, well, you know, we can just go over here and, you know, compute the radius of convergence just like we did back in section 8. It's going to be infinity. Sure. And then infinite radius of convergence, all reals. Okay. So that would be like if you just had a WebAssign problem where they said, you know, compute the interval of convergence. Well, you know, you use the definition I gave you in the theorem. Okay, and so we'd be like, okay, we understand this, we understand where it converges. So that part you already know how to do. What I'm doing is now I'm taking that idea and saying, is it actually true that if we let n pass to infinity, that this is actually the function e to the x? That's what I was saying in the theorem. And that's the subtle point that most students never get in this class. And it's not surprising because it's actually, you know, it's a mature concept to figure out. So even if you're working with power series, maybe you're solving differential equations, you know, with power series, you may get some crazy series and you won't even know. You won't even know what the actual function is, but it exists as an infinite series. But if we want to do a construction with a known function and then go to the next level to say that the infinite series is actually this function, then this is what we have to do. So we've thought about this, then we come over here and say, well, what's going on with this? Now we can fill this in. Notice now, for all levels of derivative, we just get e to the x. So this will just be e to the z. So that's all we have to do there. And now we can move this forward. Then the limit, and we can just look at the absolute value because we have the absolute value theorem. If we can show the limit of the absolute value is 0, then we have the limit of the non-absolute value function equaling to 0. That was what we learned back in section 1 of the very beginning of this chapter when life was a lot easier. So we'll look at this. So we have the limit as n approaches infinity, e to the z, n plus 1 factorial, x, always got something on the desk, plus 1. And now, of course, we can look at the absolute value of e to the z, which is just e to the z. So we're going to get to use our special limit that we proved back at the, again, in section 1, that nice special limit that I said later on down the road, this will be very useful. So now, of course, relative to n, e to the z is a constant. So we can factor that. And then we can move the limiting process inside by continuity of the absolute value function. So the actual sequence limit we had was just x to the n divided by n factorial, but there's no loss in generality replacing n with n plus 1 in the power and the factorial. And so now this limit we actually know it's 0. So this was the special limit that we proved using the squeeze theorem. This is a special limit. So even with that, we still have to have other artillery to solve this problem. And so now we have the absolute value of 0, which is 0. So e to the z times 0 equals 0. So indeed, this will actually be true for any x. And that's good because the interval of convergence here is all real numbers. So this is true for all x real. So now we can unequivocally state, so if and only if, e to the x is precisely this infinite series. So the idea here is that once we kind of put this to rest, we don't worry about it, and you can do the same for sine and cosine. So I'll just say similar arguments. Similar arguments for sine x, cosine x. Now, why are these nice? I mean, of course, when the derivatives are well behaved, this is a magnificent way to do it. But we worked with tangent. You know, that was not fun. I mean, just giving the fifth order derivative of tangent was a task. It wasn't difficult, but it was a bookkeeping exercise, and lots of times we can't avoid the bookkeeping. I mean, it's just part of working with arithmetic. So now when we look at our setup here, the geometric, they get taken care of automatically. So we've got the first three. We've got e to the x, sine x, cosine x. We're going to talk about the binomial theorem, which again will take into context the arc sine or the inverse sine. We have the inverse tangent. So this list means something to us now because we spent time generating it. So it's kind of like, you know, you have a list of antiderivatives, an interval table, and we generate that too. I mean, the best way to review anything is start at the foundation. I had a teacher in high school, a French teacher, Miss Cooley. I've talked about her before. She was one of the best teachers I've ever had in my life. She says, Ron, if you need to review something, you got to read it. You got to do it. So she'd say, if I've got to teach French 3 or 4, then I need to read French during the summer so I'll be prepared for my students. She taught me a lot of techniques that are actually valid in math. But I say this because we had the same idea about teaching. You've got to hit at the foundation. And my parents thought I was going to double major in French because I took a lot of French at the University of North Carolina because it was just like doing math. But I eventually got tired of it. I mean, it only takes so much, and then I'm not planning to live in Canada or France or whatever. But be that as it may, you always have to go back to the foundation and just build it up. That way you check off everything, keep all the ducks in a row, so to speak. So now we're thinking, okay, so we have to kind of dim the lights and say, okay, the fun's a little bit over because we've got this hugely important theorem called the binomial theorem that you hear about in pre-cal when you've got positive integer exponents. But then when you get to calculus, you want to jazz it up a little bit and make it a little bit more usable as far as your calculator goes. So if we want to basically verify our list for the binomial theorem, we have to work a little bit harder. because we find out that the derivatives aren't as user friendly. And so we just have to look at a different technique. So here's a theorem. This is called the binomial series. And yeah, this is basically like the geometric progression, um, uh, Pythagorean theorem. This is one of those linchpins that if we didn't have, we'd struggle quite a bit. So this is the binomial theorem. And Newton devised this and stated it this way. That is, one, so we'll start this off like I did the last discussion, where we're just kind of blindly going through this and keeping our fingers crossed, and then show that what we were doing actually did make sense. So 1 plus x to the k. So, and I'm going, my first example, once we build this, it's going to take a little while, will be the 1 plus x to the 1/2, the square root. So for instance, this is an odd series, but very important. We got to talk about binomial coefficients. So 1 plus x to the power k will be n equals 0 to infinity of k choose n, the binomial coefficient, times x to the n. So this is basically a Maclaurin series, and this will work for any k on this interval. Now, if k is a positive number that is greater than 0, then we can get this to work at the endpoints. I'll say more about that later. Well, let me just go ahead and just give you some ideas here, because the convergence here is much more complicated at the endpoints. We don't really have the theory. You have to use a more advanced test. And one of the tests is called Rob's test, which kind of ascends beyond the ratio and the root test, because if you apply those and get 1, you don't get a conclusion. So Rob's test or other tests that are, well, Rob's being the most usable, or other similar tests, take you to the next level and allow you to assess convergence at endpoints when tests that you would normally think would work fail. And so what we'll just say here, number 1, if the power k is a positive number, then we get convergence here. We can include the endpoints. This is extremely important. It's not going to be the case that I mean, this is kind of fixed and it can be shifted around, but this will be something you can use, especially if you're in a physics class or a differential equations class, because Rob's test really is something you don't see until you take advanced calculus. I'll mention it and show something about it, but it's a more subtle test. So now 2 would be, for instance, if k lives here, that is k is between -1 and 0. We can get convergence at 1, but not at -1. So basically, this is convergence. So if we did 1 plus x to the 1/2, we could include the endpoints. On your chart, it says dependent on k, and this is what it's talking about. And then, of course, the rest of them we don't really care about, so we'll just say that's it. That's all I need to say. I don't need to add any more. So you get this for any k. Let me just write here, for any k. You always get this, but you can improve it for positive k or k between -1 and 0. Otherwise, you're here and that's it. So if you're working a problem on WebAssign and the k is less than -1, then you're like, okay, well, all right, I don't get the endpoints, but I still get that. So that's something, again, this is a little bit more subtle, and I'll just say requires more subtle convergence tests. We've seen when we get divergence, then we don't need special machinery for that. The divergence theorem is so powerful. I mean, when it works, boom, we're done, and we don't have to have anything that's elaborate. Now, one thing I wanted to talk about in this particular case is look at the radius of convergence. But first, what I want to do is just remind us of the factorial definition of the binomial coefficient. So by definition, and I'm going to use the one that's easiest to use, not the one that we can use without going crazy. And we're going to use the ascending factorial, even though sometimes it's written backwards. It's just too hard for students to understand. So I'm just going to say here for k n, and we're going to take n to be an integer. K is any real number, but n is an integer and it's non-negative. So for instance, n could be 5, 1, 2, 3, 0, 1, 7, 8, 9, things like that. K can be anything. So we're going to define this so it works for any k, not just the positive integers that you saw in pre-cal. So this is going to be k, going to write this as ascending. Or in this case, in this particular case, I'm going to write this as descending, descending. So I'm just going to write out a couple of terms. And so the final term, or the final factor we're going to get in of these, will be k minus n plus 1 divided by n factorial. So what we see here, normally we try to preserve this for the case n greater than or equal to 1, because normally what we have is, like, if we have k choose 0, we define this to be 1, since we're going to think of 0 factorial as defined to be 1, just to keep division from 0 out of the way. But when we write this, it's usually most convenient to think of n greater than or equal to 1. So for instance, when we start out with n is equal to 1, we just get k, we just get the first one. We just get k, and 1 factorial is just 1. So k choose 1 is always k. So here's a little sidebar. K choose 1 is always k, just by definition. Okay, so that reminds you of Pascal's triangle from pre-cal when things were a lot easier. So now, if we think about this, in terms of just this definition, what we see with the binomial theorem, ladies and gentlemen, is that we have to be able to, you're thinking, well, okay, I can just compute these, Professor Ron, and I've got a few coefficients and I'm done. And isn't that good enough? Well, we need to move it a little bit farther than that, because we need to be able to work with this arithmetically like we have here. But let me just give you an example, then we'll compute the radius of convergence. So here's a simple example. This is one we're actually going to end up doing. Say we have 1/2 choose 2. So basically, we're going to let me give you just one more notation here that will be even more helpful. We're going to think of this as k perm n over n factorial. Now, the idea here is, even though this is descending, we're going to think of this as n factors. So you start with k, and the nth factor is k minus n plus 1. So if I did this one following this would be 1/2 perm 2 divided by 2 factorial. So this also, not only does it give you the denominator, but it gives you how many factors that you're going to get with the k. Starting with k minus 1, that's 2 factors. If we needed 3 factors, it'd be k minus 1, k minus 2. So this notation here even though it varies throughout mathematics, I actually learned this as an undergraduate in probability because the professor was a big combinatorics guru. And so he liked using this, and we kind of, you know, took it on and thought, okay, fine, we'll keep this notation. So when you look at this, you get 1/2 and then 1/2 minus 1 over 2 factorial. And so now if you look at this, okay, well, we're not going to be fancy to factor this right now. We'll just keep it plain Jane. This will just be 1/2. And then, of course, 1/2 minus 1 is negative 1/2 divided by 2. Well, now all the 2's come downstairs and we have a negative upstairs. So you just get 2 cubed. So you get negative 1/8. So if you have to compute binomial coefficients, ladies and gentlemen, that's how you do it. So you're thinking, well, the theorem tells me, you know, the theorem tells me how to do this, and maybe I'll just believe it. Well, that's a whole lot to believe. So the idea here is the computation of binomial coefficients for our use in this class will revolve around this definition. And of course, if k is a positive integer, this series is finite, because then this doesn't go on forever. They start to terminate, just like you had with Pascal's triangle in pre-cal. So 2 choose 2, that would just be 1. So when the k is an integer, positive integer, no problem. But now we've got, now of course, when we look up here, we would see that this particular series for this k, so you can just say here, k equals 1/2. We would actually get convergence at the endpoints. Okay, again, verification with Rob's test. And I'll tell you what that is eventually. So now what we want to do is, before we actually use this, is prove that this is actually valid. So first what we want to do is compute the radius of convergence. We need to verify that it's 1. I mean, we're told it's 1. So here we'll say R will just be the limit as n approaches infinity of a sub n, just like you did with the power series, divided by a sub n plus 1. So a sub n, excuse me, we have a sub n, so that's going to be k sub n, or k choose n. And then we'll say times, we'll do 1 over. And then n plus 1, so we have k choose n plus 1. Right there. Now, so I have plenty of room, I'll just move down to another sheet. So here, what we want to do is just continue with this. So I'm gonna write to here, and then I'm gonna move to another sheet. So now, if you like, spread this out so you can see it. K choose n we have right here. So we have k minus 1. And then we have k minus n plus 1 divided by n factorial. And now we want to flip this over. So this just gets flipped. But now instead of n factorial, we have n plus 1 factorial. And then downstairs, we do the same thing. We have k minus 1. And now n gets replaced with n plus 1. So the very last one will be k minus n plus 1 plus 1. So we'll leave that here. So now we're thinking, okay, well, let's go ahead and pair things up and rewrite them. So we have, let's put our n factorials together. So this will be n plus 1 times n factorial. And here we just get what? N factorial. The n factorials will absorb. So you put these, pair them up just like we do with the ratio test. And then we have k minus 1. We'll go down here. Now I'm going to go ahead and reduce what's downstairs before I decide how far I'm going to go here. So we have k minus 1. And now notice we distribute the minus 1. So we just get k minus n, but then the negative 1, the positive 1 absorb. So we get k minus n. Now notice, as we look at these and we think about this, we get, we decrease by 1, we decrease by 1, we just whatever. So notice this term here is bigger than this term here is bigger than that. Or let me say it one more time. As we move through the list, the terms get smaller by 1, the factors. So this is smaller than this by 1. So what I'm going to do is in the next step, I'm going to use that observation. So here I've got what? K minus n plus 1. So notice the way I've written this is descending. So each factor is 1 less than the previous factor, okay, when we're descending. So this is 1 less than that factor. So the factor before this, again, what is it going to be? Let's just think about it. So we have n plus 1 over 1. And so here, if this is, as we move up and as we move down, notice here, that's not going to help us. But this, in this case, is 1 less than the previous factor. So we have to add 1 to this to get the factor right there. So that's going to absorb all of these. So that's the logic here. That's why any of this works. And so when it's in this form, it's not too difficult. So we're going to have k minus 1. Then we have k minus n plus 1. That's the factor right before this one. And then, of course, k minus n. Because notice, these just decrease by 1. These just decrease by 1. So again, if I decrease this by 1, then I get this term. So this must be the term previous to this one. That's all I'm saying. So now, and I always get mad at my pre-calc kids, they still use slash lines. I don't want to see any slash lines on your work. I can see little boxes. Boxes are fine. That's or you can underline things. That way you don't slash through the work. So notice now, all of these factors absorb and we're left with k minus n, just using the fact that we have this descending definition. And it's actually very helpful. That's why I'm using it. So now this gives us what? And I've left, let me go ahead and put in the limit sign. Professor Ron gets focused on the algebra, but we know we're always doing a limit. We're in calculus, right? We're always thinking about a limit. So now we have n plus 1. And then we have, if you like, just write the negative n first. Negative n plus k. Now we can run the limiting process inside by continuity. K is a constant. So these are the dominant terms. So this will just give us ratio of leading coefficients, which will be 1 divided by negative 1, which is the absolute value of negative 1, which is 1. So that's really what we thought would be the case. That is, the radius of convergence for this particular series here is indeed 1. So that makes sense. So we know we get that. at least for whatever this is, okay? So, and I'm saying that because we don't know. We don't know. We don't know that this converges to that. We haven't proven that. Okay, that's why the whole basis of this lecture today, and this is one of the most subtle lectures we do in this class. And I do it so that you'll actually move to the next level and go into engineering math with some understanding aside from rote memorization, which gets you nowhere. I guess unless you want to go to medical school, and that's great. We need good doctors, and gotta know that the parts of the anatomy and all that. I mean, that's important. So there's a place for everything. So now, and I'm maybe some of you are future biomedical engineers or you know, PhD MDs. I've got a colleague from my undergraduate years who's an MD PhD. So work for him, and he loved math. So good for him. So now when you look here, you're thinking, okay, well, this is even better. Now, what we want to do is think about what does this do for us? And this won't take much time. But if we start taking derivatives, like you know, we get these factorials and we don't get something that's going to be easy to analyze. We're like at the point of Rob's test where it's like, well, you know, I can't kind of teach you advanced calculus in 30 seconds. So I've got to try a technique that will allow us to get this proof with doable effort. And so here's what we're going to do. First, and let me just go ahead and start with the clean sheet, because I always run out of room. We're going to observe, how can we get this started? We want to basically show that we can derive a constant function that will do what we want it to do. So if we take f of x, basically f of x is this series here. Oh, wrong series. Let me state this formally. In your notes, this is what we're calling f of x. So you have this. I just don't want to write it on the paper. I need all the room I can get. That's what we're calling f of x, ladies and gentlemen. And so if that's f, we want to show that that is actually equal to that. So if that's what we're calling f, we want to show that this infinite series is actually the binomial. That's what we're showing. So now let's observe the following. So you know what f of x is in abstract. And let's look at this. So I want to compare f of x in abstract, which is an infinite series, to the function 1 plus x to the k, and take its derivative. Let's use the quotient rule. So this will give us f prime of x times 1 plus, right when it was easy, right? Calculus 1 minus f of x times k times 1 plus x to the k minus 1. Just using the power rule, derivative of the inside being 1. Divide by 1 plus x to the 2k. Okay, now just to, as a little aside here, I'm going to do a little calculation over here. But now let's go ahead and factor the k minus 1 copies of 1 plus x. Right, so let's factor that. 1 plus x, k minus 1. So we've got what? F prime times 1 plus x, and I'll put that in brackets so you can see it's just multiplying f prime times 1 plus x. Here, minus k times f of x. And so we get 1 plus x to the 2k. Now, of course, this is what I wanted to use, just use the laws of exponents, but it might be a little bit hard to do in your head. So just say k minus 1 minus 2k. Again, in this particular case, this will give us a minus k minus a 1. So that's the new power, but we're going to take everything downstairs to eradicate the negatives. So we get something like this. Let's put the k first. It's better to put the constant k first. And then, of course, if we take everything downstairs, this is 1 plus x to the k plus 1. Now, this is the key here. For g of x equals f of x divided by 1 plus x to the k. We know this. G of x is a constant if and only if its derivative is 0. If and only if the numerator here is 0. So we get f prime times x times 1 plus x must equal k times f of x. Now, what we're hoping, we're keeping our fingers crossed, is that the constant g, excuse me, the function g will be a constant 1. And if we evaluate the constant that way, that would just say that f of x is equal to the 1 plus x to the k, and that would prove it. So this is a differential equation here. There are many types of arguments for this, but most of them, ladies and gentlemen, are overly complicated and don't really get at the heart of the matter. I love this argument, and I actually was made aware of this argument as an undergraduate at the University of North Carolina when we were using Swakowski calculus. And the beauty of this argument is that it uses stuff you already know. It doesn't venture outside of that. So now if we look at this, then this will take us back to here to give us the constant. And if we can evaluate the constant to be 1, then we're done. Indeed, f of x, the infinite series, would be equal to this function. So this is a roundabout way, excuse me, running in the cold, but I love it anyway. Let me get a swig of water. Sorry. What we're saying here is that this is a roundabout way of getting to the fact that the infinite series actually equals the function, but we're not using the theorem where we say that the remainder goes to 0, because the derivatives are just too complicated and don't, again, give us a type of analysis that would make sense to us at this point. And so this is a standard argument. So now we just have to show this, and I've set this up. If you look at your class notes, I have one argument there, but I've streamlined this argument to make it even simpler. So all we have to do is show that this equals this. And this will be good practice for differential equations. So we got to work with some infinite series. So let's do it. 1 plus x times f prime. Now remember, f prime is the infinite series. So this gives us 1 plus x. I just thought of a way to make this argument a little bit quicker than the long-winded one by, excuse me, making sure that we do this quicker without having to build it completely. So I've reworked how I set up this argument to kind of bring this into the argument quicker to give us a way to move through the algebra more easily. Now, of course, when we do the prime, we're going to get n equals 1 to infinity. remember, in this particular case, let me just write this here now that I have room for it. That's what we started with, but it's been a while since I've written it. So we're going to take the derivative term by term differentiation, and we'll start at 1 because the n will come down and they'll give us a 0 term. So we just have n, k, choose n, x to the n minus 1. So that's differentiating term by term. So what I did, I wanted to wait until we expand this to make it as simple as possible. So now we're going to multiply this series by 1 and by x, just like you've done in your homework. So in the first one, we get the following series, this multiplied by 1, so it doesn't change. Excuse me. And now multiply by x, so we'll have the x to the n minus 1 plus x, or times x, will give us n. Now, one thing that we want to do to make this all look nice and beautiful so we can push everything together is align these powers. So we want to add these series as long as the powers are the same. So that's the first thing we're going to do. We're going to replace n with n minus 1 with n. So we're going to make this bigger, so we have to make this smaller by 1. So we're actually re-indexing. So now we'll get n equals 0. So this is what you'll do with the power series solutions in differential equations. So it's the reason I teach this. Oh, and now, of course, let me just make room for the n plus 1. Speak, say 500 things at one time. So now this basically says replace n with n plus 1. So the n becomes n plus 1. And then, of course, we have to change it here. Sorry, I get speaking, and then I write things with the wrong ends. So we get n plus 1, and then, of course, x to the n. So again, n becomes n plus 1, so we get n plus 1 times k, choose n plus 1, x to the n, and we start at 0 now because if we increase this by 1, we have to decrease this, the index, by 1. So it gives us 0. Plus, now we have n equals 1 to infinity. This doesn't change. Now notice, when we look at this, this is good. We've got the same power here, but we've got one term here that we don't have here. We have the n equals 0 term. So let's write that down. The n equals 0 term will just be what? 1 times k, choose 1. That's just k. So notice this doesn't have the 0 term, so we just write it off to the left and now put the two series together. So now they both start at 1. And so we have this. So we have n plus 1 times k, choose n plus 1. And these are nice identities, but we're going to just work them out because you don't know the identities. And if I used them, they wouldn't make any sense. So now when we look at this, when we put these two series together, we have the same power of x, and then we've got these two different coefficients, n plus 1 times k, choose n plus 1, and then n times k, choose n. And this is where we get to use our definitions of the binomial coefficients, and we just have two basically strings of the coefficients to work with, and then we can narrow it down very quickly. So now, k choose 1 times 1, that's k. So this k just hangs out. So now, let's go ahead and use the definition. And in this case, I'll put the n plus 1 over to the side. So for right now. And so we're going to have k minus 1. And then we get k, we've seen this before, k minus n plus 1 plus 1. So we've seen that before. That's why I did the radius of convergence, so at least this wouldn't look so foreign. And then we have, I'll go ahead and put the n plus 1 here. And then we have the n plus 1 factorial. So now if you like, let's see here. Yeah, let me go ahead and remind you what that is. Notice the 1's absorb, and this just gives us k minus n. That little curly brace looks pretty bad, sorry. And then we have plus, so we have k minus 1. Now notice we're going to get the same thing before. We're going to get k minus n plus 1. And remember, this term is the one that's right before, because as we start moving, you know, we see that each of these decrease by 1. So we get the same argument that we have with the radius of convergence. And then of course we have the n times the n, and then n factorial, x to the n. So we got the k. And then we're just going to factor this, but I want to write this out. So notice here, we've got the term right before this is 1 bigger. So we have k minus n plus 1, which is right there. So let's go ahead and write that in. Since that's k minus n, the term right before it is k minus n plus 1. Now that n looks kind of bad. Notes to look good. And then we have k minus n. And now, if you will, the n plus 1 will absorb the n plus 1 first factor of the factorial to give us n factorial. So now the denominators will be the same. And I could have left out this step saying, oh, you know how to do this. And then, of course, let's see here. Yeah, but I wanted to write it in. That way it's clear to everybody. And now when we factor, we're in good shape. So we have k plus notice this part here and this part here are the same in both. That's just k choose n. So this equals k choose n. K choose n. So we can factor that. So factor the k choose n. This is a very elegant argument, but the only hard part is what I've done 2 or 3 times already with this. That's the only part. And writing it this way, you can easily see that as they get smaller each time, we can back up 1. And so that's the key to doing this argument. And I've shortened it so much. And so now we get what? K minus n plus n times x to the n. So what I've done is push the arguments together to make them a little bit cleaner so they don't take so much time. So now notice the n's absorb. And so we just get k times this. So k times k choose n, x to the n. but that's just k times almost, we're almost there. So this will be k, factor the k out of both of these. Now, this is what you do in differential equations. So you need to see this before you get there. Otherwise, you feel like you've been harpooned. But now, of course, that's just this. That's f of x right there. Notice that this is the zero term here. K choose 0 times 1 is just 1. So that's the zero term. So this is just this. Where we start at 0. But that's just k times f of x. So indeed, 1 plus x times f prime is k times f of x. That's what we wanted to show. That's the meat of the argument right there. That's the linchpin of the argument, which is based upon this. So if you think about this first, ladies and gentlemen, this part flows, and it makes the arguments quicker as opposed to dragging it out. Now, so our next test, like I say, there'll be maybe some multiple choice questions on this, covering this material. I'll find some way to work it into the test. And so now, when you look at this, we see now, let's just see what we have here. So this implies, well, I can move this out of the way. So now, too many sheets here. So we see that in this case, that g prime of x is indeed 0, because it's 0 if this is true, because that makes that 0. So if and only if, in this particular case, g of x equals a constant c. So this is what, by definition, f of x divided by 1 plus x to the k equals a constant. So now, if you will, just to make it simple, we can pick a simple value in the interval of convergence. We know it works for 0. So let x equal 0. And f of 0, well, let's just look at it. This will be n equals 0 to infinity. K, choose n, 0 to the n. But notice this is the 0 term, so this is just 1. The only term that survives is the k choose 0 term, where this is just 1. So it's just 1. And then, of course, 1 plus 0 to the k is just 1 to the k, which is 1. So then f of 0 divided by 1 plus 0 to the k equals 1 over 1 equals 1 equals c. If and only if f of x, which is the infinite series here, k choose n, is actually the binomial. So the thing about this is that we know x lives here from the radius of convergence. And so we just pick 0, like I've done many times in the problems, just to move the problem forward more quickly. So what we're seeing again is that even though this took a little bit more time, we have this very powerful result that makes our calculators work. So now, ladies and gentlemen, you can see that when it comes to working with convergence, sometimes we have an easier path. Others we have to be creative. And so we don't have to spend a lot of time on abstract ideas. We can certainly know that 99.9% of everything we've done is based on material that I have taught you. And then of course the Rob's test is just a way to look at things in a more refined level to one up the ratio test. The ratio test is a great result, but it has limitations. If we get one as a limit, we don't know. And so the Rob's test is just a refinement. It's like Abel's test. There are all kinds of great convergence tests that you study when you take advanced calculus or real analysis. And some of you may do that. And they're lots of fun, and they're great. They're great for engineers, but most engineers don't want to do that much math, but that's okay. So now let's look at an example. So when you think about the example I was talking about, let's look at our friend, the square root of 1 plus x. Now all of these are done the same way, ladies and gentlemen. You already know how to substitute in the list. We've already talked about that. That's the easy part. The binomial theorem is the most difficult part of this section, aside from just accepting the results. So what you'll have to do in WebAssign is that they'll say, use the binomial theorem to write this Maclaurin series. So the binomial theorem gives us an automatic Maclaurin series, but what WebAssign wants you to do is analyze the binomial coefficient. That's the key. So for instance, what we want to do in this particular case, and let me write this down, use binomial theorem, and I'll show you a way to do this to keep it reasonable. Use binomial theorem to write a Maclaurin series for, in this case, f of x. We'll just use our friend. We square roots are at the center of what we do, or just put the radical if you want. So we know, what do we know? Well, we know a lot. That's a loaded statement. We know 1 plus x to the 1/2 is the infinite series n equals 0. So if I don't do the proof and I don't work with these binomial coefficients, you won't know how to do them, and you won't know how to do these problems. So WebAssign really does, Dr. Larson has a really ingenious way of taking this theory into the level that Calculus 2 students can understand, where you actually promote some good learning. And some of you in computer science will take more combinatorics than deal with the binomials. So this will be 1/2, choose n, x to the n. Okay, so now we're thinking, all we really have to do is analyze this guy and we're done. Now we know from Rob's test, which I told you at the beginning, which was the checking the endpoints, that since k is bigger than 0, note k equal 1/2 is positive. This implies we get convergence at the endpoint. So that's a plus. If I have time to say more about Rob's test, I will. That's kind of icing on the cake, but that we get this by Rob's test. Now, one thing that's interesting about all of this is that now you know how to analyze this. So let's just do a little sidebar. Let's just analyze this, and I'm going to remind you of a nice little theorem that we have. Before we do this, let me write this over here. One, this is the theorem I was telling you about. We can get a string of odd positive integers. Now, as far as computing, you're thinking, Professor Ron, you showed us how to compute these things. I'll just do a few and be done with it. That's fine. But I want you to get your WebAssign right. So now notice this has a factorial, this is a factorial identity. This is actually going to be the following: 2n factorial divided by 2 to the n, 2 to the n times n factorial. That's a nice little identity there. You can prove this by induction or algebraically. Usually because it's n's, it works better that way. So we'll just say here that n is greater than or equal to 1, because we don't really care otherwise. So the thing is, these occur a lot with binomial expansions, and so we want to be able to use them along with the factorials. So this will be a credit, and WebAssign gives you this formula as you work through these problems. Now let's look at this. Let me move this down a little bit so I don't run into that. So we need to analyze this. So we'll just take this away from the series and analyze it, so we don't have to write down a series 500 times. So now we'll just use the definition. So this will be 1/2 minus 1. I'll just write down several. 1/2 minus 2. And then we have 1/2 minus n plus 1 divided by n factorial. You know that we've already used this several times in our arguments today. That's your new definition for the that of a binomial coefficient. K is any number, n is a positive or a non-negative integer. So now when we look at this, we're thinking, well, we can dress this up a little bit. If you like, we've got n factors here, and notice this is n minus 1 factors. So I'll just do a little dressing up. So this will be 1/2. And I'm just going to go ahead and get a common denominator here. 2. So 1 minus 2. And then 2, 1 minus 4. So what we're going to do is generate a -1, a -3, a -5, etc. And here we're going to get a 2. So this is going to be a 1 minus 2n plus 2. Okay. So now we're thinking, okay, we're almost there. So notice we're going to get all these 2's downstairs. And then, of course, we've got the n factorial. Let me do my fraction bar. I'll go ahead and just do the long fraction bar for now. And now notice we've got n of the 2's, and we can go ahead and factor. For n minus 1 factors, we have a negative, which we can kind of turn around. But for right now, let's note that this will just be what? Negative 2n plus 3. So we almost got to that factor. We got to the one right before it, okay? So we've got this here. So now out of each of these, factor a -1. So we're going to get 1, -1 to the n minus 1. And we've got the 1 here that's just kind of hanging out right there. I'll just write it in so you don't think I just completely ignored it. Not like it's going to matter. And so here we have a 2 minus 1, which is 1. So notice here, when we flip these around, we're going to get a 1. Well, I'll write it down this time. I'll be real meticulous this time. n minus 3. And then, of course, all the 2's downstairs, we have n copies of those. So we have 2 to the n factorial. Okay, so this is what you have to do with these, and you'll get good at it. Just what I'm doing here. But you think just plain old square root would be simple. Okay, now notice this is the 1, the 3, the odd progression. So we have -1, n minus 1. So now we've got, if you like, times, and I'll just do 1 times 3. I'll stick in the 5, that'd be the next one, to 2n minus 3. So of course, we just want to make sure that the signs are correct. So you could put n plus 1 there if you wanted, but I just have n minus 1 negative signs. I've got n factors, but n minus 1 of them have the negative that I can get rid of. And so now when we look at this, we have 2 to the n factorial. Now we want to use our nice little identity here. So we're gonna multiply and divide by 2n minus 1. So we have to pay the piper. So now I can use the factorial identity here because we added this. So we'll just say use identity. So now when we look at this, everything is in good shape. We can use our identity and have a nice, neat formulation of this. Of course, this is fine, but it doesn't tell us much. This gives us a nice formula. You may say nice, I don't know about nice, Professor Ron, but it is different. So we have negative 1 to the n minus 1. And now we can use our newfound friends. So upstairs, we're going to have 2n factorial. And then we divide by 2 to the n times n factorial, but we already have a copy downstairs. So now we have 2. So when we multiply, we get a square. 2 to the n factorial squared times 2 to the n minus 1. So that factorial, just that stray factor is there because we have to have it. So now this is what I'm talking about. I chose this one. This is actually not directly from the WebAssign. This is one of my favorite functions of all time. Well, I have a lot of favorite ones, but this is the technique that you have to do when you want to write a binomial series to produce a Maclaurin series. Now, when I've been doing this, ladies and gentlemen, I've pretty much been looking at this as n greater than or equal to 1. So the idea here is that when I get 0, this doesn't really make a whole lot of sense. This is really just focusing on n greater than or equal to 1. And depending on the way the coefficients develop, that usually makes it a little simpler to write. And WebAssign will kind of guide you to that to say, okay, the first term is 1. Now you put n equal 1 and greater with the summation. So they guide you through that. So now here's the coefficient that we were looking for. That is, this binomial coefficient can be written this way with the factorials. Kind of neat, right? So now this implies equivalently, now we know that 1 plus x to the 1/2 does equal this. We just proved that. This equals 1. So that'll be our first term. So we kind of neglected the n equals 0 term, did this for the n greater than or equal to 1 plus. Now we throw all this into the series. So we have n equals 1 to infinity, and put all this in with the x to the n. So we have negative 1 to the n minus 1, 2n factorial, 2 to the n times n factorial squared times 2 to the n minus 1 times x to the n. Now you can stick the x to the n upstairs in the numerator, or just write it out to the side, your choice. I don't care, same thing. And we know that we get convergence with Rob's test at the endpoints. So there's your WebAssign problem. This is how you manipulate the binomial coefficients. That's all you have to do, ladies and gentlemen. It's the difference between, okay, you know, you can sit here and generate coefficients, okay, and that's doable. And when you're doing approximations, you'll need to do that. But you have the choice now that you can use these formulas here to generate the coefficients. So maybe a little bit easier, but also a reworking of the complexity of the binomial coefficient. Binomial coefficients are in no way simple, but with this definition, if you're thinking about probability, you're thinking about counting, but now we're not always thinking about probability because this is not an integer here. So we get the series for the square root of 1 plus x. Now what I did, ladies and gentlemen, is I had a little, did a little computation here. Let me show you, just with the Google calculator. So I generated some coefficients with this formula here, okay? So you can verify this. So for instance, when we do these, you can generate coefficients. So let's do this. So again, say we want x to be equal to 1 to approximate square root of 2, okay? So we would have 1 plus 1 to the 1/2, which is square root 2. So what I've done here is I've used our formula, our newfound formula, to generate some of these numbers for us. So first, a sub 0, that's 1. A sub 1. And what I've done, I'm going to use the formula that we have here. Let me write it down so you can see it. We'll just go ahead and use this. So we get this for free. So let me write this so you can see it. And then for n greater than or equal to 1, we'll have a sub n. I'll just repeat this from the previous page of notes. To n factorial. So for a sub 1, you're going to get 2 factorial divided by 2 squared times 1. That is, note when n is equal to 1, so we'll just say n equals 1. We've got negative 1 to the 0, which is 1. 2 times 1, 2 factorial. And then we have 2 to the 1 times 1 factorial, that's 2, so 2 squared. And then we have 2 minus 1, which is 1. So what does that give us? Well, that's just 2 over 4, which is 1/2. Now let's generate a couple more. A sub 2, n equals 2. So let's just go ahead and fill it in. This will be negative 1 in this case. And another thing that you want to do when you actually look at these is don't worry so much about this. If you want to replace this with n plus 1, it's the same thing. Just make sure that we start out with the right parity, so to speak. So here we get a 1. So here we've got what, 2 times 2, so that's a 4 factorial. And then of course here too, we get what? We get a 4 times a 2 factorial squared, then times a 3, okay? So now, if you like, we've got the negative. So I'll write out some of these and then others I'll just have you verify. So we have 4, we've got a negative 4 times 3 times 2, and you can put the 1 if you want. And here we've got 4 squared, 4 times 4. And if you like, this is just an 8. That might be a little bit quicker, but just go ahead and write it as 4 times 4 times 2 times 2, squaring the 4 times 2 times a 3. So here's what I want you to do. Just kind of like, you know, put little boxes around them, absorb, okay, absorb. When you write up your work this time, I want to see this. I don't want to see slash lines. If you put slash lines on your work, I put a 0 on the paper. I mean that. I never use slash lines. I don't want to see it. Oh boy, get me riled up, put slash lines in your work. And then the 4s, they absorb. So now that gives us a negative 1/8, negative 1/8. My pre-cal students are learning this. They think they're being slick by slashing through their work. They have a lot to learn. So a sub 3, let's do this one. So now we're going to get the 2 here, negative 1 to the 2. And now 3 times 2, that's a 6 factorial. And then here we've got 8 in this case, and a 6 factorial, or 8, or 3 factorial, which is 6. And then 6 minus 1 is 5. So that's a positive 1. So 6 times 5 times 4, 3, 2. And so now we have an 8 times an 8 and a 6 times a 6 times a 5. So now you see the drift, and I'll write down a couple more that you can verify, but I just want to show you how simple it is using our new friend here, which is easier than starting from scratch with all those fractions. This avoids the fractions. So the 5s go away. And let's see, we've got a 2 times a 3, that's a 6. And we got this 6. So we're left with a 4. So this is a 4. 2 times 4 times 8. The 4s go away. And we just get 1 over 16. Now I've gone ahead and computed a couple more. I went ahead and computed a sub 4 and a sub 5. I think here. Let's see, I've got a sub 3. And let's see, what else did I compute? Let me check here. So we've got the a sub 5, I got that. Yeah, a sub 4. Let me write this down. I knew I had computed it. A sub 4, and you can verify this. This is going to be a negative 1 to the 3rd, and you get an 8 factorial, 2 times 4, and then you get a 16 times a 4 factorial, which is 24. In this case, times a 7, 8 minus 1. And in this case, I got a negative 5, you can verify this, over 128. I want to work another example. And then I actually did a sub 5, same thing. A sub 5 will be a negative 1 to the 4th power. I've got a 10 factorial, 5, and then you've got 2 to the 5th, 32, and then 5 factorial is 120 squared times a 9. And when I reduce this, ladies and gentlemen, I got 35 over 1,280. That's where I got basically, 320 times 4. So that works. So now what we can see is, and this is not the best approximation, I just gave several decimals. So square root of 2 will be approximately, so let's just write them down. So remember, x equals 1, so all the powers are 1. So just add up the coefficients, 1 plus 1/2 minus 1/8 plus 1/16 minus 5 over 128 plus 35 over 1,280. And this will give you approximately, I'll use my Google calculator, 1.42578,125. So this will secure the 1 decimal place with the square root function. So that's how your calculator works. Now, like I said before, there are adjustments that are made to the computations, but this is why indeed the binomial theorem is of such importance. No one understands now how your exponent key works until you actually know this theorem. And this is a monumental result in analysis that makes the computations of square roots or radicals arithmetic. So the idea here is that when you do the binomial theorem, you use your, if you need it, your identity for the string of the odd integers. If you need it, adjust for it if there's a reason to use it, and just the basic definition of the binomial coefficient to rewrite the binomial coefficient in a more user-friendly way. So you're thinking you could have just done all these separate calculations with binomial coefficients, but it would have been much harder. This is easier because you just can absorb factors. And you don't have to worry about terrible fractions because we got rid of the fractions. We made it user-friendly. So this equals this. Okay, when we're starting with n greater than or equal 1, then we have our 1 out here for the a sub 0. Okay, so that's an elegant problem to say the least. Now, let's just say that okay, so we know how all of this works, and we're like, oh, Professor Ron, this is a lot of work. Well, no, it isn't. Compared to what we did last time, this was actually pretty easy. So what I want to do now, just remind you that if you need to write a series that has a sine squared, you know the series for sine, a Maclaurin series, so you can use the power reducing, and a lot of students forget this. So for instance, and here's a hint, this will help you later on down the road. You know this, it's not like we haven't used this 1 million times. Sine squared a, or x, is 1 minus cosine a over 2. So if you needed a Maclaurin series for the square of the sine, you can use the power reducing and just write this series with the cosine series. And so you've got your 1/2 minus 1/2 times this series. So the beauty of the list is that you can use identities you already know. So this provides an easy, excuse me, Maclaurin series for instance, sine squared. So you can, and then of course you could replace sine x with 2x and get the square of sine 2x and have a beautiful series with little or no effort using the list. So that's extremely powerful. And of course, being able to analyze the coefficients for the binomial series now makes that series usable. And you can, in general, the binomial theorem is extremely complicated. Okay, there is nothing simple about it. There's nothing simple about extracting square roots. I mean, where would we be without the calculus? We would not have STEM. We'd have some other degree that you'd be pursuing. Okay, so here's an example of what I just talked about. I want to estimate, or we want to estimate this integral. So if you looked at this integral in Cal 2 or Cal 1, you'd say, oh, I'm done, I'm cooked, I can't do this. That's not a standard integral. We'll say with error less than, say, 1/100. Now, when you look at this, you're thinking, well, this would be impossible using substitution, that we don't have a differential here, so we're kind of cooked. But we have our series, power series list, and we have term by term integration. So so the key is use power series list. And we're good to go. So now let's do it. So we know, so e to the x equals this. We'll write down several terms. I'll just write out the factorials as numbers. So we prove this. We know this is true. And you do the same for sine. We've beaten that list up. Okay, we know this is equal. So now we can do term by term integration, and that is replace x with, so we're going to get an alternating series, negative x squared. So the power of math is using the power series in a way that cuts down our work. So now we have the, what is it? Integral 0 to 1. Now we don't have to worry about changing to t because these are both numbers. So we don't have to do the t variable. It's not needed. So you can be sloppy here and not have to worry about it. So we have now, notice here, this will be the integral e to the negative x squared will be n equals 0 to infinity negative x squared to the n factorial dx. How neat is that? We're doing algebra 1 here, and we're actually doing calculus. So now flip it. So now, if you want, you can go ahead and dress this up a little bit. So go ahead and factor it first. So this is going to be a negative 1 to the n, x to the 2n, just to clean it up a little bit. So just factor this, the negative, so it becomes alternating. So now we have add 1 divided by the new power. Never thought your Cal 1 would come in this handy. All right. So now notice when we replace the x with the 0, this just zeroes out. I mean, we've got the 1 here, so we don't have a 1 hanging out like we did with the binomial because we've raised this by 1. So that the lower limit zeroes this out, and we're just left with the upper limit, which is this. How neat is this? So we just have 1 to the 2n plus 1, which is 1, so we get this infinite series. So what you're seeing here, ladies and gentlemen, is this integral here, which is this guy here, equals that. And you're thinking, well, thank you, Professor Ron. I've replaced a difficult integral with an infinite series. How simple is that? Well, as an engineer, as a computer scientist, as a mathematician, you can now approximate. So we just want to see, well, we want how many terms? We're going to start at 0. So if we find an n, then we have the 0 term 1 up to n, whatever, like we've done before. So let's look at the first neglected term since this is a alternating series. So we'll do a sub n plus 1. So the first neglected term will be negative 1 to the n plus 1. The alternating series is a blessing. I mean, we can't get any better than this. This is easy. I mean, the integral test requires an improper integral. So we're glad for this. And so here, let's see here, we've got 2n plus 1. So we've got what? So n plus 1, n plus 1. So 2n plus 2 plus 1. So that's 2n plus 3. So again, replace n with n plus 1. So that gives us n plus 1 factorial and 2n plus 2 plus 1, which is 2n plus 3. And so this equals what? 1 n plus 1 factorial 2n plus 3. Now, if you look at this, we want this to be less than 1 over 100. So equivalently, just reciprocate both sides. So we have n plus 1 factorial times 2n plus 3 greater than 100. Now, if you look at this and you think, you know, what can we do with this to check it out? If you look, if we have like 1 or 2 or whatever, we can start with that and see which will work. But for instance, let's just check or just test. Let's see here. Let's try n equal 2. So we have what, 2, so this is 3 factorial. And here we have what, 4 plus 7, or plus 3, that's a 7. And that's going to be what, 6 times 7, which is 42. And that's too small. Let's try n equal 3. Let's see here. So n plus 1, so we got n. Okay, n factorial. Good deal. So n equal 3. So we've got, let's see, what, 4 factorial, 24. And here we've got 3, so that's going to be a 9. So that's going to be 9. Let's see, oh, here we go, 20 plus 4 times 9. So again, n equals 3. We have 4 factorial, which is 24. And then we have 7, 4 plus 3. Sorry. So we've got 4 plus 3. Excuse me, we've got 6 plus 3. Sorry, kids. That'll be a 9. So that'll be a 180. Well, so that gives it to us 180 plus 36, which will give us 216. And this is greater than 100. So now what we can do is we can now see that if we start this particular progression, we can get what we need. So notice, so we're done. It is sufficient to use, let's see here, there we go, n equals 3. So now we see the first, so n equal 3 for our partial sum. Now, so that, what does that mean? So we can use the first term, 0 term, the first term, the second term, the third term. So this means, in this particular case, that we can add the terms up this way. So we'll say S sub 4, which equals, and so we can go over here and add all these up. So this will be 1 minus, now here we will get, let me just write these down, n equals 0, n equal, let's figure these out, n equal 1, n equals 2, n equals 3. And so for the 1 term here, let's just see, that's going to be a negative. So we get 1 times 3, so that's 1/3. And then for n equal 2, we've got plus, so we got 2, and we got 2 times, in this case, that'll give us a 5, so that's a 10, 1/10. And then for the 3, we get a negative. So we've got what, a 3 factorial, which is a 6. And then here, let's see, we've got a 3, 6 plus a 1, 7, 1/42. So this would be sufficient. So the idea here, when we look at this particular problem, this is just like what we've done before. We look at the first neglected term, so to speak. That is, when we look at our series here, we see that the terms are generated this way. And so as we start writing out the terms, we want to see, well, how good is the partial sum? Well, it's only as good as the size of the first neglected term. So for instance, we think for the first neglected term, if we want n plus 1, that would be past the n that we need. And so we replace n with n plus 1. And so here, of course, n plus 1, n plus 1, and then n plus 1 here gives us a 2n plus 2 plus 1, which is a 2n plus 3. And so now when we look at this, we just say, okay, this needs to be less than 1 over 100. So we reciprocate. All of these are positive. So we have n plus 1 factorial times 2n plus 3. And that means this needs to be greater than 100. So we test like we've done before. Now, just remember, sometimes you can actually solve these equations, but it might just be the case that all you need to do is test. And so what we do is we just start testing to see where we actually get an inequality that works. When we try n equal 2, we see that it doesn't work too well, but when we try n equal 3, we see that we do get a number that exceeds 100. So again, the idea here is we can use what we already know about power series from our list to do a calculation that in most instances would be impossible. That is, we use the power series and the term-by-term integration to get an approximate value for a series that would otherwise be extremely difficult. So what I wanted to do today, ladies and gentlemen, is to show you kind of basically how everything just fits together. From the very beginning, we start with sequences and we move all the way to the Taylor series, and we see how that impacts convergent power series in general. Every convergent power series is its Taylor series. Then I'll show you how to compute intervals of convergence. I'll show you how to figure out how to check endpoints using real series convergence. And then we use the geometric series to compute power series using an alternate approach. And then after that, once we connect the convergent power series with the Taylor series, we can generate a list here. We can generate a list, use that list when we need to, and then also we can actually look at the binomial series in a similar manner, again, computing coefficients and approximating things. So now we're ready to say goodbye to the infinite series for now, but at least now you know why your calculator works and you know how all of this fits together. So at this point, we're going to say, thank you, infinite series. We had a good time. And then we're going to move on to parametric equations and polar coordinates. And so that's going to be a nice change of pace. So again, if you want to go ahead and look at that section, you're certainly welcome to, but it'll be refreshing, I think. And it's going to be a nice introduction to curve theory that you will take in Calculus 3. So I've enjoyed teaching this section. It's one of my favorites, and I hope that you have likewise enjoyed it. It's excellent material, and it makes a calculus student become an actual math student. For the first time, you're actually learning the mathematics that drives your calculator and actually drives STEM, okay? So thank you, everybody. Have a great day, stay warm, and if I don't see you at office hours, I will see you next class. Thank you.